Hey guys, welcome to our lesson on 6.1, Math 112, angles and their measures. So before we can talk about angles and their measures, we have to define what an angle is. I mean, we all kind of know, but let's really get it defined fully for ourselves. So very simply put, sorry if there's any announcements, hopefully they don't show up on the screen. We're trying new things. So very simply put, an angle is formed by rotating a ray about its endpoint. The starting position of the ray is called the initial side, and the final position is called the terminal side. Okay, so we have our rays. That's how we denote that it's an angle. And so this right here would be our initial side, and this would be our terminal side. Now, just the same way that we typically use x to represent most base variables, we use the Greek letter theta to represent a measure of a random angle. So theta looks like that. It looks like a circle with kind of a squiggly line through it. Now, depending on which way we rotate our angle, will determine whether it's a positive or negative angle. Sorry about this. Okay, so counterclockwise gives us a positive angle, while clockwise gives us a negative angle. So if our angle is rotated like that, that represents a positive angle. Whereas if it's like that, that represents a negative angle. Okay, and that's really important to understand kind of whether it's positive or negative simply is kind of counterclockwise or clockwise. Now the endpoint of the ray is called the vertex. Okay. Now, what's really important with angles and is talking about them in what we call standard position. So standard position, let me write this out. Standard position is when the initial side is the positive x-axis. So if we draw our x, y axes, that's our initial side, that is a positive angle theta in standard position. Okay, good. Now, how do we talk about the measure of an angle? We talked about what an angle is, whether it's positive or negative, but how do we talk about the actual measure of the angle? Well, very simply, we use degrees. Okay, and so if we rotate all the way around from the initial side all the way back to the initial side, in degree measure, that would be 360 degrees. Okay, and so that gives us one full rotation. So that means 1 degree is 1/360th of a complete rotation. 180 degrees would be half of a complete rotation. Now, there's a couple special angles. It doesn't matter if they're in standard position or not, but an angle that measures between 0 and 90 degrees is called an acute angle. And anything that goes between 90 and 180 is called obtuse. Okay. Good. Now, there's a few special angles that have some special names. So something like this, 360 degrees. Okay, so that's one full revolution. Okay. If we have an angle like this, So that would be 180 degrees. We call that a straight angle, since it makes a straight line. And then the last main one we'll talk about is this guy here, which this is a 90 degree, or simply a right angle. Okay. Now, what's really cool is that two angles could have different measures, but they could have the same initial side and the same terminal side. And what we call those is coterminal. Okay, so what would that look like? Well, let's do this in standard position because that's the nicer way to do things, right? So what if I have, so my side here, and we'll give ourselves a nice x-axis. So what if I have like this angle here? All the way around. So that is one angle. Well, this is another angle. They have the same initial side and the same terminal side, but they're different measures. One of those is positive, one's negative. So those are coterminal angles. What if I'm looking at something like this? So this is 60 degrees, okay? But what about this angle? That angle is 420 degrees, right? Because what we did is we went one full revolution around, and then we went another 60 degrees. So if one full revolution is 360 degrees, and then I go 60 more, we end up at 420 degrees. So what's cool is we can find any coterminal angles simply by adding or subtracting a multiple of 360 degrees. Pretty nice, right? So that is a very useful thing to be able to identify whether two angles are coterminal. That is something that will be a very big deal later on in this term when we're dealing with trig functions on angles. Okay. Now, this is going to be a definition we're going to kind of slowly parse through. I'm going to read it first, and then we'll parse through it. So an angle that has its vertex at the center of a circle and intercepts an arc on the circle equal in length to the radius of the circle has a measure of 1 radian. What? So note, the angle subtended at the center of the circle measured in radians is the ratio of the length of the arc and the length of the circle's radius. This means that radian measure is dimensionless. Okay, so let's just break through all of this. Okay, let's start with the first base definition. So we have an angle that has its vertex at the center of a circle. So let's draw ourselves a circle. Okay, we have an angle with its vertex at the center. If that vertex, so if we get an angle here that has, so let's say this right here is length r, and this right here is length r, okay, then this angle theta is 1 radian. Now radians, the second part of this is a very kind of confusing thing, but basically what it gets to is that radians are dimensionless, okay? And there's, yeah, I just don't really know any easier way to put it, but it's just kind of odd. Yeah, just kind of leaving you hanging on that one. It's not really a big issue. I'm not worried about it enough to try and explain it to you in a way that's going to make sense. If you're curious about this and it's really kind of sticking in your craw, Google why are radians dimensionless. Okay. So I'm going to draw an angle, and I want you to try and think, what is the angle measure in radians? So again, I'm going to start with the circle. Okay, and let's say we've got this angle here, and I know that this is 4, and this distance here is 12. So then what does theta equal? Well, so I want you to pause the video and think about this. See if you can figure out what theta equals. Go ahead, pause it. Come on, actually do it. Try and do it. Okay, welcome back. So we have that one radius along that arc. If our angle intersects an arc sector of 1 radius, then that angle is 1 radian. So that means since the radius here is 4, for every 4 I go, that gives me 1 radian. So there's 4, there's 4, and there's 4, right? Because 4 plus 4 plus 4 gives me 12. So each one of those is 1 radian. So that means I have a total of 3 radians. So this angle that I've drawn here is 3 radians. Okay. Now think about this. How many degrees are in one full revolution? 360 degrees, right? Perfect. What's the circumference of a circle? Right? For those that don't remember, right? The circumference, right, is pi d, right? Or 2 pi r. So what that means is in one full revolution of a circle, so one circumference of the circle, there are 2 pi radians. What that means is that 360 degrees is equal to 2 pi radians. That's awesome. So that means 360 degrees is equal to 180 degrees is equal to pi radians. So we can use that to create a conversion factor. And to convert from from degrees to radians, we multiply by the factor pi over 180 degrees. And to convert from radians to degrees, we multiply by 180 degrees over pi. Now, very simply put, we want to think about trying to cancel this out, right? So if I have, say, 360 degrees, and I want to convert this to radians, I'm going to multiply this by pi over 180 degrees because our degrees cancel each other out. If I have, say, 2 pi radians, I'm going to multiply this by 180 degrees over pi, so my pi's cancel out. Okay, now pi is not a unit here. It's actually the number pi, the number 3.14, but it can kind of work that way for us. So we can kind of build that up. So how many radians in a complete rotation? Well, we already talked about this, right? There are 2 pi radians. Easy enough. All right, let's convert the following. So some of these are easy, some of these are less easy. If we look at these, all we have to do is simply multiply by those conversion factors. Okay, so because I want to convert to radians, I need there to be radians in the numerator. So I'm going to multiply this by pi over 180 degrees. Now 180 and 180 cancel out, so this is just pi radians. Okay. Now I am missing something here. Okay, well, deal with that later. So now I've got 150 degrees. So this one's not quite so simple, but it is still very simple. So I need to multiply this by pi over 180 degrees. Okay, our degrees cancel out, and what I'm ending up with is we can reduce this very simply to 15 over 18, but we have our pi still. And hey, those are both divisible by 3, so I can reduce this even further, and I end up with a lovely 5 pi over 6. So we have 5 pi over 6 radians. And yeah, these are pi radians. So it's that easy. Now what about this? 4 pi over 3. I want to convert this into degrees. So I need to multiply by 180 degrees over pi, but the pi's cancel. And what I end up with, okay, is 4/3 times 180. Now, if we divide 180 by 3, so we kind of focus on this aspect here. We're not cross multiplying, we're just focusing on that. 180 divided by 3 gives me 60. So what I end up with is 4 times 60, or 240 degrees. Sorry, 60 degrees. There we have it. 3 pi over 2. Again, because we have that pi, we are in radians already, we need to cancel that out. So 180 degrees over pi, cancel those. 3 times 90 degrees, because the 2 and the 2 goes into 180, 90 times, right? And that gives us a lovely little 270 degrees. Okay. Nice. That's not too bad. Now, here's an example of using radians and coterminality. Now, something that you guys may be tempted to do is to look at this and go, okay, cool. So I've got 3 pi over 5 radians. I need to find something coterminal. So I'm going to convert this from radians to degrees, add 360, and then convert back into radians. But that's a whole lot of mess, right? We don't want to do that. What we simply want to do, okay, to find the measure of the least positive angle that is coterminal with 3 pi over 5. So what does it mean, least positive? So if, let's just say, for instance, 2, and I'm doubling, right? So then 4 would be the least positive double of 2. Okay, I know doubling, that doesn't really make sense, but 4 would be the next kind of thing. So we don't want to add 2 revolutions. We want to just add 1 full revolution. Okay, and so what we're going to do is we're going to take 3 pi over 5 and add 2 pi. So what's nice is both of these have a pi, so I can actually kind of factor that out, and I get pi here, and then I have 3/5 plus 2. Oh man, fractions. When we add fractions, we have to get common denominators, but we're in Math 112. That's easy, right? Because this is just like 2 over 1, so we multiply by 5, and we get 5 times 2 is 10. So when we add the fractions with both having a denominator of 5, we get 3 plus 10, and so what we end up with is 13 pi over 5. Now, if you're looking at me and looking at this going, oh my god, huh? Don't worry, you have a calculator. You can use your calculator. Get to know your calculator and your fractions features. You can do that there. Now, the next problem, find the greatest negative coterminal angle. Okay, so the greatest negative coterminal angle would be simply to subtract 2 pi, not to subtract 4 pi or 2 pi twice, like take away 2 revolutions, but just do it once. Okay, and so actually, before we get to this, let's draw this. So this is our first angle here. So 3 pi over 5 sits right about here. So then 13 pi over 5 sits right about here. Nice and easy. Okay. Let me make that a little prettier for you guys. Let's go red. Red is, whoa, 3 pi over 5. Blue. Sorry, 13 pi over 5. Nice and pretty, right? We always like pretty drawings. So now to find the greatest negative coterminal angle. So we're just going to simply do the same thing, 3 pi over 5, but since we want it to be negative, we're going to subtract 2 pi. So again, we can just do it very simply. So I have 3/5 minus 2, right? We have our pi out there, okay? Well, again, it's 2 over 1, we multiply by 5, right? So now I have 3/5 minus 10/5. So that becomes negative 7/5 pi. Okay. or negative 7 pi over 5. And that's the way I'm going to write this because that's how I want you guys to write it. Negative 7 pi over 5. So if we look at an example of that, okay, so this right here is our 3 pi over 5. This negative 7 pi over 5. See how this is kind of working out? We're getting there. We're making some progress, making some sense out of some of this, hopefully. So this is a really kind of important skill to understand and to get used to is finding these coterminal angles, and something that we're going to do heavily on the homework is identify whether things are coterminal or not. Okay. So now sketch negative 7 pi over 5 in the correct quadrant. Well, we just did that, right? So this should be really easy, but how do you know? Just looking at this, how do I know if it's in the correct quadrant or not? Well, let's just think about kind of our full axes. So here, this would be like 0 or 2 pi. Okay. Oops, sorry. Over here, up here would be, or sorry, let's go all the way. Halfway over would be pi, right? Because if going all the way around is 2 pi, going halfway around must be 1 pi. So going half of halfway, so a quarter of the way, would simply be pi over 2, which makes this right here 3 pi over 4, right? Because pi over 2 is a quarter turn, so if I go pi over 2, then there's 2 pi's over 2. Sorry, this is not 3 pi over 4, this is 3 pi over 2. 3 pi over 2. So we go pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, which is just 2 pi. So when we're looking at negative 7 pi over 5, the way I think of this is first I go, okay, it's negative, cool, so it just goes backwards. But so I look at 7 pi over 5. 7 is bigger than 5, which simply means that this number here is bigger than pi, which means if I were positive, that would mean I'd be more than this. Now, it's not super clear if it's more than 3 pi over 2 or not, but we can use our calculator to check if is 7/5 greater than or less than 3/2. And so we find out that that would come, if it was positive, would come in the third quadrant. 1, 2, 3, 4. Yeah, 1, 2, 3, 4. But since it's negative, it's actually going to come around here. Okay. Now, the best way to do this is really to kind of just get familiar with this. And it's something that we're just going to get more and more practice at doing and kind of finding its relation to these values. Okay. Looking at the relationship of whatever we're looking at with these 4 numbers to kind of see what ones it's between. And that's going to give us a rough estimate of where it's at. Okay. All right. Now, this is something that I'm going to very, very quickly cover because, quite frankly, I don't like it. It's not something that I really find to be very mathematically useful. It's really only used and involved to give math teachers some unique problems to do, but I don't like it. So fractions of a degree can be measured using minutes and seconds. So this is back to degrees. So we're not in radians anymore. We're in degrees. So what we say is that 1 minute, so if we have a single apostrophe, that's a minute, that is equal to 1/60th of a degree. Okay? To go here. That's all terrible. Let me rewrite that. 1/60th of a degree. So that means that 60 minutes is 1/60th, so that's just 1 degree. 1 second, okay, that's 2 apostrophes. So 1 second is 1/60th of a minute. Okay, so that means 60 seconds is equal to 1 minute. Wow, we are feeling really crazy here. So 1 second, 60 seconds is equal to 1 minute, just like normal time. So if we want to convert 22.46 degrees to degrees, minutes, and seconds, well, we can simply break off the minute, or the degrees. So we have, 22.46 degrees is 22 degrees plus our 0.46 degrees. Now, the way we deal with that is we take our 0.46 degrees and we multiply that by 60 minutes in 1 degree. Okay? And so our degrees cancel. Degrees cancel. So we get 22 degrees plus, then 0.46 times 60 gives us 27.6. So 27.6 minutes. Which is 27 minutes plus 36 seconds. So if you take 0.6 times 60, you will get 36. And so what we end up with, this final notation that we use, okay, is 22 degrees, 27 minutes, 36 seconds. Gross. I hate it. Oop. Oh, I just exited out. All right, cool. We'll pull that right up. Just going to scroll down. Scrolling. Okay. Convert 108 degrees, 45 minutes, 36 seconds to decimal degrees. Gross. But let's do it. So what we're going to first tackle is we're going to tackle our 36 seconds by multiplying that by 1 over 60 minutes. Okay? Or sorry, 60 seconds. So 1 minute or 60 seconds. Our seconds cancel out. And we get very nicely that 36 over 60 gives me 3/5 of a minute. Okay. We do a similar thing. So we have our 45 minutes and we multiply that 1 degree in 60 minutes. Okay. And what happens there? Well, minutes cancel. And we get 3/4 of a degree. But wait, we still have this 3/5 of a minute, so we need to do that again. And it disgustingly turns into, so we multiply this, 3/5 of a minute, 1 degree over 60 minutes, and the minutes go away, and we end up with 0.01 degrees, and 3/4 is 0.7, well, that was bad, 0.75 degrees. We had 108 degrees, so plus our 0.75 degrees, plus our 0.01 degrees, which comes out to 108.76 degrees. Yuck. Okay, that was the extent of what I'm going to do, minutes and degrees and all that garbage with you guys. If you guys are going to go into sailing or any sort of aviation, you're going to learn this better, and you're probably going to have equipment that does this for you, so you don't really have to do it. But hey, I'm done with that. So now we're going to talk about some special angles, some complementary and supplementary angles. This is something that you're going to totally get mixed up, and so it's very important that you have this written down somewhere and have it somewhere easily accessible in case I ever mention this again for you. Okay, so we simply say that two angles are, jumped around on my page. Two angles are, whoa, complementary if their sum is 90 degrees, and two angles are supplementary if their sum is 180. Okay? So find the complement and supplement of 43. Very simply, so complement would be, so we'd have 90 degrees minus 43 degrees. And that gives us 47 degrees. So if this right here is 43 degrees, then this angle here is 47 degrees. The supplement is 180 degrees minus the 43 degrees, which gives us 137 degrees, and that just looks if this is 43, this is 137. Quick quiz for you, refresh. 43-degree angle is what type of an angle? That's right, acute. An 137-degree angle is a what? That's right, obtuse. Awesome, you guys are so brilliant. I'm so proud of you for paying attention. I'm sure all of you guys got those questions from me right when I answered them, right? Okay. Complement, no, sorry. Skip, I don't want to do it. I'm not doing that with you guys. So, this one here is a little more important, okay? Say that the arc length, which we denote with the letter S, intercepted on a circle of radius r by central angle theta in radians is given by this very nice equation. So there's a couple things I want to unpack here, and we're going to unpack them in just a minute when I kind of get an image for you guys, but we're going to start simply with our formula. So this arc length S is very simply equal to r times theta. That's it. It's really easy. So we have our circle, okay? So this arc length that is intercepted on a circle of radius r by central angle. So what does that mean, central angle? Central angle just means that the vertex of our angle is at the center, okay? So this is angle theta, this is r, that's s, okay? Very simple. A quick note, just for those of us who like to live in reality, r is greater than 0. The radius is a measure of distance, and distance cannot be negative, okay? Now, if any of you want to get wise with me and talk about physics or anything like that, think of moving backwards. That is not distance. Okay. And as noted, let's see here. We're gonna use our galaxy pen for this. Theta is in radians. Okay. I did all that fancy stuff to it, so it should be kind of obvious that it's important. If theta is in degrees, this does not work. Yeah, I would have to convert whatever degree measure angle that is into radians. Okay. So let's look at an example. So if a circle has a radius of 5, and we want to find the length of an arc intercepted by a central angle of 240 degrees. What did I just say? We can't do this, right? Because theta is in 240 degrees, but it has to be in radians. Oh, but wait, that's right. We just talked about our a little bit ago. We can convert degrees to radians to degrees, and go all crazy with that. So let's do that first. Oops, we don't want that. 240 degrees. To convert that to radians, I just multiply by pi over 180. And what does that do? 4 pi over 3. For those of you who are going like, oh my gosh, how does he do math so fast? I did this problem already before, and I've got it written down next to me. So when you guys are doing this, feel free to take a second, grab a calculator, do 240 divided by 180, convert that to a fraction, and see where you're at, okay? The nice thing about converting to radians is pi is always going to be in the numerator, always. When you convert into from radians into degrees, okay, the pi's should hopefully cancel out, but what if you had something like 2 radians? Then the pi isn't going to cancel out. So it's kind of important to be aware of that, okay? So we now know our angle measure in radians, Okay, so 4 pi over 3, 4/3, that's bigger than pi, but not quite pi over, or 3 pi over 2. Okay, and we just think, what is 4/3? It's 1.33. 3 halves is 1.5. So what I know is if I have a circle, and what if that circle just happens to be centered at the origin? Man, this is convenient for us, right? I know that this angle has to end up somewhere in here. Okay, so let me backtrack just a little bit, get a little bit better imagery for you. So that angle there, that's theta. Okay, so if, whoa. So if theta is equal to the 240, which is 4 pi over 3, so this is our theta. So what we're looking for is, we are looking for, what is this length? So this is our length, S, no matter how terribly my covering is. Well, all we have to do is very simply follow the formula. So do this in blue, because I can. S is equal to R theta. What's R? I don't want my sticky notes up. No. Go away. R is the radius, which in this problem here was 5. Okay, awesome. So I get that S is equal to R theta, which is equal to 5 times 4 pi over 3, which is 20 pi over 3. But wait, what are my units? Well, if my radius was in centimeters, then my arc length is going to be in centimeters. So this is 20 pi 3 centimeters. And there you have it. Okay. So to simplify this thing for you, this would be one of the more complicated problems you deal with because you had to do this nice little conversion here first. Okay. Make sure your arc or your angle is in degree or is in radians. It's not in degrees. Let's restart. Blah, 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 blah. Okay. Make sure that your central angle that you're talking about in this arc length problem is in radians. As long as it's in radians, you simply multiply it by the radius, and that's your arc length. Okay. So, definition number 6. Angular speed measures the speed of rotation and is defined as okay. And I am blanking on what this W is called. World's called W. It's the Greek character. And I can't remember what it's called right now. Sorry. I had a lot of technical difficulties today, and this is a late video. So, W is equal to theta divided by T, where theta, measured in radians again, is the angle of rotation at time T. Linear speed is given by V equals R times W, where R is the radius and this W is radians per unit time. Okay, so what we're doing here is we're using this to kind of measure what the linear speed is of an object on a rotating thing, such as, hey, example 16, the Earth. Okay, so kind of what this is talking about, if we have this object that's rotating in space and we've got this thing here, what's its linear speed? It's kind of that straight shoot off speed. Okay, so if the Earth rotates one complete revolution every 24 hours, it has an equatorial radius of about 3,963. So that's the radius at the equator. For those of you who are super geo nerds, I love you guys. You guys are awesome. The Earth is not exactly perfectly spherical. Obviously, we've got mountains and valleys and, deep abysses in the ocean. But even if you were to kind of fill all of that in, it's still slightly squished and kind of oblong-ish from the equator. So we go with usually an equatorial radius like this. So the first thing we want to do is find the angular velocity of a person standing at the equator in radians per hour. Well, very simply put, W equals 2 pi over 24. Why did that give me a diamond? Okay. And very simply, that simplifies to be pi over 12 radians per hour. Okay. So we know that we complete one rotation. One rotation gives us 2 pi in a 24-hour period, giving us a time of 24. Okay, not too bad. Now, estimate the linear speed in miles per hour at the equator due to Earth's rotation. Well, that linear speed or velocity is r, the radius, times this w. So here, that is equal to r times w, which is 3,963 times pi over 12. Okay, which now if you get out your calculators, that is approximately 1,037.51 miles per hour. That's pretty fast. Why are we not flying off the Earth? Gravity, right? The good old apple falling on someone's head. Okay, we are getting there. We're almost done, guys. Stick with me just a little bit longer. Okay, this is our last page. I believe our last page. Almost our last page. Okay. So, A, if you want to be grammatically correct, a sector of a circle is the portion of the interior of the circle intercepted by an angle. Okay, so what does that mean? Well, we've got some circle, got an angle. This is the sector of that circle. Okay, the area of a sector of a circle, okay, of the sector A of a circle with radius r and central angle theta in radians is given by. It's a nice little formula. Okay. A is equal to 1/2 r squared theta. Okay, not too bad, not too scary. So, if we note that the area of a sector is proportional to the measure of the central angle, okay, so we can look at this proportion. So if the area of the sector, which is over theta, okay, so pi r squared be an angle of 2 pi, okay, so pi r squared is the area of a circle for those of you who forgot, and theta would be the full revolution. So if we went all the way around, we would be talking about the sector of the entirety of the interior circle, and that simplifies to be 1/2 r squared. So what we get is the area of a sector, if we multiply both sides by theta, is 1/2 r squared times theta. It's just the derivation of this formula. If it doesn't make sense to you, it's okay. But what we just said is that the area of a sector divided by theta. So if we go all the way around, so we have one full revolution, we were talking about the entire area of the circle, which the area of a circle is pi r squared, and a full rotation is 2 pi. Simplify that, we get 1/2 r squared. That's how we come across it. Let's do an example. Okay, so a circle has a radius of 5.5 inches. Find the area of a sector if its central angle is theta equals 225. What do we have to do? That's right. First thing we have to do is convert our angle from degrees into radians. So let's do it. It's so easy now, right? Because we are getting annoyed with this. Whoa, okay. Focus, there we go. So we get that 200 and, oh my goodness gracious. Okay. 225 degrees times pi over 180 degrees. Our degrees cancel. And we get 5 pi over 4. All right. So 5 pi over 4, we can kind of think of this the same way. This is again going to end up in the third quadrant. So we have a circle. Our angle is something like this. Here's our theta. So what we're trying to find, I'm going to use yellow because it's the easiest color to not see. So what we're trying to find is this area. So to do that, we simply follow our equation. So the area is equal to 1/2 r squared theta. So that's 1/2 times 5.5 squared times 5 pi over 4. Now that's a whole lot of math to do, but we use our trusty handy dandy calculator to do it. We hit those buttons. And what do we get? We get 59.4 inches squared, right? And that's an approximation. Okay. Now why inches? Because the radius was in inches. Okay. Now if you want to go exact with this, well, we can do that, and we can say that that is 605 pi over 32 square inches. Pretty neat, right? I know you guys are all excited now. Okay, what about this? Find the area of the workspace for a robotic arm that can rotate between angles of theta 1 equaling negative 40 degrees and theta 2 equaling 80 degrees. Okay, you can change its length from R1 equals 5 to R2 equals 25. So they have been nice enough to draw us this nice little image. So what we have here is two areas. We've got the area that they have shaded, and then we also actually have this other angle, this other area here. So if we find the area of this outer edge, we have to subtract this area of this inner edge. Okay, so that image is not the best because that does not really represent accurately what we are doing. So what I'm talking about is if our theta at 1 angle is negative 40 degrees and theta 2 angle is 80 degrees, why is this spread out so far? My guess is this is a typo or a change of problem. So let's change our image to match our problem. Okay. Why am I still in red? Let's go back to black. Okay. So negative 40 degrees gets me about here. Negative 40 degrees. 80 degrees gets me about here. Okay. Since 90 degrees is a right angle, that's right up. Now, we have our two radius of 5 and 25, okay? So what I need to do is figure out what this total angle measure is, okay? And then I need to figure out what the total radian angle measure is. Now you can do that either way. We can either convert to radians and then figure the total, or we can figure out the total and then convert to radians. It really doesn't matter. Just for funsies and practice, let's convert to radians and then add, because you guys all love adding fractions, right? So we have negative 40 degrees. So we want to multiply that by pi over 180 degrees. And when we do that, we get negative 2 pi over 9. We also have this 80 degrees. Oops. So we multiply that by pi over 180 degrees, and we get 4 pi over 9, which makes sense, right? Because 40 is half of 80, so 80 is double 40, right? So doubling those numbers, we get, yeah, so that makes sense. Now, how do I add these together? Well, I don't just add them, right? Because then I'd end up with 2 pi over 9, which isn't correct, because this one here is negative. So what I have to do is I have to very calmly take 4 pi over 9 and subtract negative 2 pi over 9. And what do we get? We get a lovely 6 pi over 9. Because right, when we subtract a negative, that becomes a plus. All right, so that is our final angle measure, okay? So for our whole space, our main theta is 6 pi over 9. Okay? So what I have to do is I have to take the area of the larger circle, or sector, and subtract the area of the smaller sector. And so to do that, okay, we need to use our lovely little angle formula, which if you remember from up here was A equals 1/2 r squared theta. Our theta is the same for both of these. The differences are r. So the larger sector is going to be our 25-inch sector. So then the area of this working sector, the total area, is going to be 1/2 25 squared times 6 pi over 9 minus 1/2 times 5 squared times 6 pi over 9. Okay, now you can do whatever you want to do. Okay, and I do realize that I have not simplified 6 pi over 9 to 2 pi over 3. You can do that if you want. I forgot to do that, so I'm just going to leave it because it doesn't change the problem. Go ahead and simplify this however you want to and kind of combine like terms or do whatever, or just very carefully enter this into your calculator. And when you do that, when you carefully enter this into your calculator, we get that this is approximately 628.32 square inches. Again, inches because our radius is in inches. Okay. Whew. Man, that wasn't so bad. I know it was a lot, but it wasn't so bad. Okay. So hopefully you guys understand that. You guys are going to get some more practice doing this on the homeworks. So get to it, head at it, have fun with it, and I will see you guys on our next lecture, 6.2. Maybe, if I can stop this recording.